In this lesson, I'll show you how to use the ratio test to determine the convergence of a power series. This is part number 2. The question reads, find the values of x for which the following power series converges. To do this, we'll need the ratio test, and that's summarized right here. The ratio test tells us that we'll take the absolute of this expression and divide n plus 1, where we sub n plus 1 into wherever we see n, and we divide it by the actual series function itself. If that's confusing to you, let me show you what I mean. According to this, we will take the limit as n approaches infinity for the absolute of our series function, where I substitute n plus 1 into here and here, n plus 1, x to the power of n plus 1, and we will divide that by the function itself, n x to the power of n. Let's go ahead and figure this out. X to the power of n plus 1 can be written as x to the power of n, x to the power of 1. If we write it out this way, x to the power of n and this x to the power of n cancel out. So we're left with the limit as n approaches infinity, the absolute of n plus 1, this part, times x all over n. Next, if we multiply this x into these two terms, we'll end up with xn plus x, and both of these have the denominator of n. This n and this n will cancel out, and if we take the limit as n approaches infinity now, we'll have x over a very large number. This means that this term goes to 0. So we're left with, after taking the limit, the absolute of x, and if this is less than 1, then it converges. Let's move on to the next. Here our series function is n factorial times x to the power of n. If you're confused about what this symbol means, make sure to watch part 1 where I showed you an example with factorials. I'll follow the ratio test where I have the limit as n approaches infinity for the absolute of our function where n's are replaced with n plus 1. So we have n plus 1 factorial x to the power of n plus 1 all over n factorial x to the power of n. n plus 1 factorial, if we expand it, we end up with n plus 1 times n factorial. If we do expand this factor, then n factorial will cancel out with the 1 at the bottom. And similarly, for the same reason as in part A, x to the power of n plus 1 can be split into x to the power of n and x. This x to the power of n will cancel out with this one, leaving us with the limit as n approaches infinity for the absolute of n plus 1, what's remaining here, and x over 1, technically, because both of these factors have disappeared. If I substitute infinity into n, I'll end up with infinity, and since I end up with infinity, according to the ratio test, this series diverges for all x values except when x is equal to 0. So let me write that down. This is equal to infinity, therefore diverges for all x values. Finally, in question C, we have this series, and once again I'll do the same thing as before. I'll substitute this and this with n plus 1, x to the power of n plus 1 over n plus 1 factorial, and then we divide this by the series itself. Now, instead of writing a line and showing the divisor like this, I'll show the division symbol, and I'll write down x to the power of n over n factorial. We're taking the absolute limit as n approaches infinity. When it comes to dividing fractions, we flip the second fraction and change the sign from division to multiplication. Now that we've done that, x to the power of n plus 1 becomes x to the power of n and x. This cancels out with this. This becomes n plus 1 times n factorial, where this factor cancels out with n factorial at the top. This leaves us with the limit as n approaches infinity for the absolute of x, the factor remaining up here, over n plus 1. And now we can take the limit. If I substitute a very large number into n, I'll end up with x over a very large number. This means that we have a limit of 0. Therefore, 0 is less than 1, so this series converges for all values of x. And there you have it. 3 more examples on how to use the ratio test to determine convergence of a power series.